Yeah. Hello everyone. Welcome back to RC Circuits. This is lecture number 3. So in this lecture, we are going to solve some more problems on first order circuits. And let's look at this circuit. So here the circuit is given and some transient behaviors at t is equal to t1 and t is equal to some tau 2. The tau 2 is the time constant of let's say this part of the circuit, and we have to find the final value, or we can directly draw what is happening for voltage across the capacitor at t1 is equal to 3.75. It means uh, this transient behavior from the switch position from A to B is happening at t is equal to t1, where t1 is, in first case it is 3.75 milliseconds, and t1 is much greater than 18.75 millisecond. Let's see what is happening in the circuit first. So initially uh, we are applying this 40 volt at t is equal to 0. This is 40 u of t, means this is the voltage. Let's say this is v1. So you are applying v1 at t is equal to 0. So there is 40 volt, and then the switch is at position A initially, and it is moved to position B at t is equal to t1. So for t less than t1, and let's say from 0 to t1, 0 less than t less than t1, we have only the left part of the circuit, this circuit. So there is 40 volt and 20 kilo ohm, 60 kilo ohm, and we have the capacitor. So this is 0.25 microfarad, and we have to find Vc of t. So first step is we need to find the time constant of the circuit. So what is the time constant of the circuit? If you short circuit this independent voltage source, so if you remember, to find a time constant, you have to replace independent sources with 0, right? So if you make that independent voltage source to 0, then this will be short circuited, then these two will be in parallel, and so across the capacitor terminals you have to find the R equivalent. So R equivalent is 20 kilo ohm parallel 60 kilo ohm, which is 20 into 60 by 80. So this is 15 kilo ohm, right? For yeah, and C equivalent is 0.225 microfarad. So the time constant, let's say this is tau 1, because we have two parts of the circuit, so we call it as tau 1, and tau 1 is C equivalent times R equivalent, which is 0.25 micro 15 kilo seconds. So this is 15 times 0.25 is 3.75 milliseconds. So this is the time constant, and Vc of t for t less than t1 is, final value is 40 volt. Sorry, what is the final value? At steady state, it will assume, the circuit will assume that this capacitor will reach to steady state to find the final value. So this will be open circuited. It doesn't know that there is some transient behavior is coming at t is equal to t1, right? So this will assume the final value as, So let's say this is V infinity is, the capacitor will be open circuited, and 40 into 60 by this voltage divider, 60 plus 20, which is 80. So this is 30 volt. So the final value is 30 volt, and the capacitor does not have any initial value, assume. So then Vc1 of t is final value plus initial value minus final value into e power minus t by tau. So which is 1 minus e to the power minus t by tau 1. So for 0 less than t less than t1, right? So will it reach to steady state better if we can draw this waveform? This. So we are seeing from only from t greater than 0, right? So this is t, and this is Vc of t. So at t is equal to 0, we have 0 initial voltage. Then it is trying to charge to 40 volt, right? So let's say this is 40 volt. So when will it reach to 40 volt? At 5 time constant, right? So which is 5 times of this 3.75 millisecond. But if you wait for that 5 time constant, then it will reach to steady state. But here we are only waiting till t1 is equal to 3.75. We will solve for condition 1 now. So which is nothing but the time constant of the circuit. So we are waiting only till time constant of the circuit, which means at this point it will only reach to, if you remember, it will only reach to 63.2% of its final value. So, or if you don't remember that, you just substitute here at t is equal to tau 1, then you will get 30 into 1 minus e power minus 1, then you will get that value, which is 63.2% of this. You will get 0.632. Then if you multiply with this 30 volt, then you will get that value. So this is not 40 volt, I am sorry. So this will reach to, if you wait for 5 time constant, this will reach to 30 volt. So 30 times 0.632, which is 18.96. Let's say which is nearly 19 volt. So we will take it as 19 volt. So it has reached to 19 volt now. Now at this point, the switch is moved to position B, and then we have this part of the circuit now, and there is again one independent voltage source which is in reverse direction compared to this one. So we will draw that part of the circuit. Okay. So there is one capacitor and 8 kilo ohm, 160 kilo ohm, and this is 8 kilo ohm, and this is 160 kilo ohm, 40 kilo ohm, and minus 75. 40 kilo ohm and minus 75. Now this is for t greater than t1. So we have 8, 160, 40. We will write that values. So Now for this circuit we have initial voltage of 19 volt, which is in this direction. So this is Vc of t, but we have 75 volt, we have minus 75 volt applying here. So at steady state, if we open circuit the capacitor, then the circuit looks like this. So the capacitor is trying to charge to its final value of this much, Vc of infinity. Let's say this is Vc2 of infinity. So 160 kilo, 40 kilo, 75 volt. So this is minus 75 because we are taking Vc of t in this direction. But since the 75 volt is in this direction, the capacitor will try to charge in this direction because there is a current flow in this direction, and this sum of this current will divide into this direction, and we have the current flowing through this capacitor in this direction. So that's why the capacitor starts to charge in this direction. So it has 19 volt initially, and it is trying to go to negative, and it is trying to go to some steady state of some negative voltage, which is minus 75 times 160 by 200. So which is 4, 5, 15, 60, I think 4, 5, 15, 4 is 60, yeah. So this is minus 60 volt, which means if you leave this circuit at this point, then this will go to minus 60 volt and it stays at minus 60 volt finally. But there is something is happening again. So we are the switch is opened at t is equal to tau 2, which means let's say for this circuit, what is tau 2? You short circuit this independent voltage source, then we left with this capacitor and this resistor block. So if you look from the capacitor terminals, then since this is short circuited, so for tau 2 you take the same circuit and short circuit the voltage source, right? So this is simply short circuited. So if you look from this capacitor terminals, then this is R equivalent. So R equivalent is this 40 and 60 are in parallel, and which is in series with this 8 kilo ohm. So 8 plus 40 parallel 160 kilo ohms. So if you calculate this one, 8 plus 40 into 160 by 200 kilo ohm. So 160 by 5 is 32 plus 8 is 40. So R equivalent is 40 kilo ohm. So tau 2 is what is the capacitor value? It's 0.25 microfarad. So 0.25 micro into 40 kilo seconds, which is 40 times 0.25 is 10, and so this is 10 milliseconds. So in this circuit, the switch is opened at t is equal to 10 milliseconds. Actually, we can take this one as t1 plus tau 2. It means uh, if it is tau 2 directly, then we are referring from this point, but after this point we have this kind of circuit, right? This is only for t greater than t1, this circuit. So after t1, if you wait for time t is equal to tau 2, which means if you wait for this time tau 2, then that circuit will reach to some value, right? Will it go to 63.2%? Definitely not, because that 63.2% of final value when we wait for one time constant is only for if initial voltage across the capacitor is 0. But that you don't have to forget, we derived that expression only assuming initial voltage of the capacitor as 0. And if it is trying to reach to final value, then if you wait for one time constant, then it is 63.2% of its final value, but which is not true in this case. So then how to find this value? Then we have to write the expression we have to find. So Vc2 of t, this is for t greater than t1, is final value is minus 60 volt that we have derived here. So final value plus initial value minus final value times e to the power minus t by tau 2. So at t is equal to tau 2 means this expression is only for t greater than t1. So after t greater than t1, if you wait for extra time constant of t to tau 2, then so you understand it. So this t1 plus tau 2 is I am referring from t is equal to 0. So that is how we generally refer, right? So minus 60 plus 79 e power minus 1. Let's see how much it is. So e power minus 1 is 0.367 times 79 minus 60. Which is minus 30.937. So let's calculate, just to show the difference, let's calculate the what is 63.2% of final value is 0.632 times minus 40. So which is 0.632 times 40 is minus 25.28. So now we will go there and see. So this is t1 and this is t1 plus tau 2, and this time duration is tau 2. So if you wait for one time constant, then we are getting minus 30.937. If we leave that, it will go to minus 60, right? So let's say this is minus 60 volt, then from here it decreases exponentially. Then at this point it has reached to minus 30.937. So minus 30.937. See, since we have already some initial voltage, it has not reached to 63.2% of its final value, right? But if this initial voltage should have been 0, then it is at this point, then it will go to uh, minus 25.28. Why? Okay, yeah. So I mean both are different in different cases. So that expression is valid only if we have uh, the initial voltage is 0. So it is reached to this value, and if you here at t is equal to t1 plus tau 2, the switch is opening. So then the capacitor will not discharge further and it stays at this voltage level, right? So we did some mistake here. Like, how did I find that mistake? So forget about the equations. So from logic, if uh, if it reached to minus 30.937, if you wait for some time constant, then with some initial voltage of 19 volt, this is case 1. Now assume the initial voltage is 0. Then if you wait for the same time, then it should have been reached to even more value, right? This is going to minus 60 if you leave at that point. If you leave that point, then it goes to minus 60. So if the initial voltage is 0, I'm saying if it is 0, then if you wait for the same time, then you will get some this kind of graph. So this should be like more than 30, right? This should be minus, like minus 30.37, or we don't know, but it should more means I'm saying in the magnitude. So this magnitude is more than that of this magnitude. So but we got 25, right? So which is wrong, because we took the final value as minus 40. I don't know why, I'm sorry for that. So we have to take the final value as minus 60. So if you take that minus 60, this is where we did that mistake. So then you will get minus 37.927. So if you do that, then yeah, you are getting the magnitude as more than this one, right? So like that is the difference between that remembering that time constant is always 63.2% is wrong. That is only true for initial voltage is 0. So yeah, so this is what is happening in the circuit. Initially it is 0, then it is going to 19 volt, and it starts charging towards minus 60 volt. So then it went to minus 30 point something, and then it stays at that point. So that is what it is happening. And yeah, this case t1 is much greater than 18.75. So what is this value 18.75? We got time constant tau 1 as 3.75, right? So if you take 5 into 3.75, then you will get 18.75, which means there is this transition is happening after 5 time constants, right? So which is more than 5 time constants. It means so this left part of the circuit is reached to steady state. After that, after it reached to steady state, then it is going to this part of the circuit. But here we did not reach to steady state, right? So what is the steady state value? It is 30 volt, right? So if you draw that graph, so case 2, then so yeah, so if let's say this is 30 volt, then we are waiting more than 5 time constant. So at that time it has already reached to steady state and it is staying at that value. This is 30 volt. So this is 5 to 1, which is 18.75 milliseconds. So now we are at this value. We have waited more than enough time. Then Then the switch is moved to position B, and we have this part of the circuit. So, and it is trying to reach to minus 60 volt, because the steady state of this second part of the circuit is minus 60 volt. And we are again, we don't know what is exactly T1 now. If we take that, then it is better. But again, if you wait for one time constant, uh, then it reached to some value, and it will stay at that value. So if you calculate that, so Vc2, I am writing for second part of the circuit, Vc2 is final value plus, now initial value has become 30 volt, initial value minus final value times e to the power minus t by tau 2. So at t is equal to tau 2, then Vc2 of t is minus 60 plus 90 e power minus 1. So you remember this e power minus 1 value, because it will come, it keeps on coming continuously, which is 0.367. So 0.367 times 90 plus 60, sorry, minus 60. Which is minus 26.89 volt. So which is even lesser compared to the previous one, right? Because the initial voltage is less at this point, which is 19 volt, but we have the initial voltage now 30 volt, and we are, after that we are waiting the same time. So that means it will reach to not even minus 30, it will reach to even lesser, which is minus 26.89. So we did correctly. That is how we can cross verify, and this will stay at that minus 26. This is negative, so it goes here and it stays here, minus 26.89. Yeah. Now we will solve this circuit. This is again a first order RL circuit, and this will be interesting problem. Let's solve that later. Yeah, we have to find I of t. So so at t is equal to 2.5, the switch is opening at this point. So before, for t less than 2.5 seconds, or from 0 to 2.5 seconds, we have this circuit, 10 volt, sorry, so there is short circuit across parallel to this one, right? So if you have short circuit and any circuit across it, then we remove this one and we take only short circuit, because the current always choose the least resistance path, right? So since there is directly short circuit, we can directly remove this one. So then we have 1 ohm and we have inductor, right? So this is short circuit. Now what is the time constant of the circuit? Let's say this is tau 1. Tau 1 is, if you remember, this is L equivalent by R equivalent. For capacitors it is for RC circuits, it is R equivalent times C equivalent. So sorry, so 0.5 by 1 ohm. If you short circuit this one, then across the inductor terminals we have 1 ohm. So this is 0.5 seconds. So if you draw the current waveform, so all this is voltage waveforms. This is Vc of t and that is Vc of t. Right? So if you draw IL of t, then from 0, what is the steady state value? At steady state, the inductor will be short circuited, right? So then we have only the input voltage and 1 ohm resistor, then short circuit. So this steady state current I infinity is 10 by 1, 10 amps. So if you take this as 10 amps, so from 0, the current will start, the inductor will start charging exponentially, and if you wait for 5 time constants, then it will reach to more than 99% of its final value, because here also the initial current is 0. So this is 5 time constants, which is 2.5 seconds. So if you wait for 2.5 seconds, then it will reach to almost 10 amps. So here also we are waiting for 2.5 seconds and we are opening the switch here. So if you open the switch, then at that point the initial value is the previous final value, which is 10 amps. So for t greater than 2.5 seconds, we have 10 volt and 4 ohms minus 30, and inductor 0.5 Henry. So the steady state value of this circuit is, if you short circuit the inductor, then you will get, so since this positive terminal is connected to this negative terminal, then these two voltages will be added. Or if you write the KVL here, then you will get the same thing. So this is I infinity. So I of infinity is those two will be added, and which is 4, which is 10 amps. Is this correct? 10. Oh, sorry, I forgot here. This 1 ohm. So the equivalent is 5 ohms. Is this correct? This is 10 volt and short circuit. This is 10 amps. And here we have 40 volt and 4 and 1 are in series. So this 40 by 5, which is 8 amps. Yeah. So in steady state, this will reach to 8 amps. And what is the time constant of the circuit? Which is if you short circuit these two voltages and if you see the equivalent resistance across this inductor terminals, so L equivalent is 0.5 and R equivalent is 5, which is 0.1 seconds. Yeah, so this will reach to 8 amps. So from 10 amps of initial current, the inductor will reach to 8 amps exponentially, and this stays at 8 amps. Because there is no transient behavior further, and this is the steady state value. So this is completely steady state, and at steady state this will be short circuited. So this expression is for this circuit the final value was 10 amps. So and initially 0, so 10 into 1 minus e to the power minus t by tau 1, and tau 1 is 0.5, so this is 1 minus e power minus 2t, right? And what about this one? This is final value is 8 amps, and initial minus final times e power minus t by tau 2. Tau 2 is 0.1 seconds, so this is 10t, right? So which is 8 plus 2 e power minus 10t. If you want to write the complete expression of IL of t, then so this part of the expression is there only till this point, right? 2.5 seconds. So if you want to write that, IL of t is 10 into 1 minus e power minus 2t times, and we have to this should be valid only till from 0 to 2.5. So from 0 to 2.5 this should be 1, and apart from 0 to 2.5 if any other value, then this should be 0. Then if you multiply that, then you will get this one. We will get to know what about this one. And after that 8 plus 2 e power minus 10t, and this is also there only after t is equal to t greater than 2.5. So this value should be 1 for t greater than 2.5, and this should be 0 for any value other than t greater than 2.5. So this is u of t, right? And if you right shift u of t, so u of t is 1 for t greater than 0. So if you right shift u of t for 2.5 seconds, if you remember, then this is, you have to replace t with t minus right shifted value, so which is u of t minus 2.5. Then if you subtract these two, what you will get? You will get only this part of the graph, which is u of t minus u of t minus 2.5. So this u of t minus 2.5 is 1 only from t is equal to 0 to 2.5. Other than that, this is 0. So if you multiply this graph with this expression, then you will get this expression only from 0 to 2.5. So u of t minus 2.5, and this one is only valid for greater than 2.5, right? So this is simple. So u of t minus 2.5. Yeah. So that is all about this expression, and then we will jump on to other circuit. So see, now we are not giving step input or any DC input. we are giving some pulse input, and we have to find V naught and find Vc also. So in this circuit, uh, so this input time period is much greater than RC. It means uh, we are waiting till the circuit reaches to its steady state value. So then -10, and this is repeating. See, this is what the time period is. I'm using that time period like this because since this is repeating, I'm just copy pasting this one, and this is also repeating. So if someone asks what is the time period of this circuit, then uh, those are t, 2t, 3t, everything, but the fundamental time period is the minimum value, minimum of uh, minimum repeated waveform. So this one is repeating, right? So we can say this is time period. Yeah. So and this is half of the time period, which is t by 2, and this is t by 2. So that value is much greater than RC. It means we can assume that it is even more greater than 5 times RC, right? So RC is the time constant of the circuit. If it is even greater than 5 times RC, it means before this even t by 2, so you can assume even t by 2 is also much greater than 5 RC, which means if you draw the Vc of t, then Vc of t will reach to its steady state, which is 10 volt, and it will stay at that 10 volt, right? Because this RC is much less than this one, and then this is the initial value from this part of the circuit. So this is moved to -10 volt, and we have initial voltage of -10 volt. So we are assuming this is even much higher than that 5 times RC. So this will again reach to steady state exponentially, and this will stay at -10 volt, and again this one. So yeah, this is how the steady state waveform looks like. So this is Vc of t. What is V naught of t? So if you apply 10 volt, then at steady state this will be open circuit. If this is open circuited, then current is 0. Current flowing through this circuit is 0, which means V naught is 0. But initially this is short circuited, which means all this input will come across this output, right? So the initial value of this is 10 volt, and finally it will reach to steady state, which is 0. And again, I mean, it will reach to steady state even before that. So it reaches to 0 and it stays at 0, and then at this point, uh, and then the input voltage is changed to minus 10 volt, and at steady state this is open circuited, and again this will be 0. So immediately after the input voltage is changed to minus 10 volt, then the capacitor is short circuited at that point, and we have this resistor. So all this complete voltage will come across this resistor, right? So this will immediately jump to minus 10 volt, and then this will go to 0 again. So like, don't assume that it was at 0 and then for this circuit again at steady state it is 0, so it will stay at 0. It is not like that. So this is 0, and again here the input voltage is changing, and it is changed to 10 volt, and capacitor is short circuited. Then again the output across the resistor will go to its input value, which is 10 volt, and again this will be 0 at steady state. So this is how the VC of VA0 of t looks like. Yeah. So this is V0 of t. So this is simple because we are waiting till it reaches to steady state, and then we are changing the input value to some minus 10 volt, and we are again waiting till the circuit reaches to steady state, and then the same thing is happening. So at steady state the waveforms looks like this one, and we can write the expressions also here. If you write for VC of t, then VC of t is at steady state. There are two kinds of waveforms, right? One is initial voltage is 10 volt and it is going to minus 10 volt, and other one is initial voltage is minus 10 volt and it is going to 10 volt. So VC1 of t is, let's assume initial value is minus 10 volt, so final value plus initial value minus final value times e power minus t by tau, 10 minus 20 e power minus t by tau, and VC2 is final value is minus 10 and initial value minus final value times e power minus t by tau, which is minus 10 plus 20 e power minus t by tau. So and this one, V0 of t is, it is simple like KVL only, right? So if you write the KVL, then you will get this input voltage minus this capacitor value, which is Vin of t minus Vc of t. This Vin of t you can write the square wave expression, and according to that square wave expression, this Vc of t is also changing. For one time period, I mean for one half of the time period, Vc1 of t is something, and other half of the time period Vc of t is Vc2 of t. So these two are different. So you will get V0 of t also. You can write that one also. V01 of t. So Vc1 is uh, initially is final is 10, initially is minus 10, which means this part of the circuit. So at that part the input value is minus 10 volt minus Vc1 of t, which is 20 e to the power minus t by tau, and V02 of t is is this correct or so this is final value is 10 volt. At this point input voltage is 10 volt and input voltage is minus 10 volt. Since input voltage is minus 10 volt, it is reaching to final value of minus 10 volt. Yeah, why I have written minus 10 here. This is input is minus 10, sorry, plus 10, and this 10 minus Vc1. And here if input voltage is minus 10 volt, then we have Vc2, so which is minus 20 e power minus t by tau. Something weird. So actually we did something wrong here. So this is not short circuited, right? In transient we replace it with initial voltage across the capacitor, right? So since the input voltage is changed to minus 10 volt, the previous capacitor was at plus 10 volt, right? It was charged to plus 10 volt and the input voltage is changing to minus 10 volt. So this stays at plus 10 volt. So at that point then it is minus 10 which is minus 20, and here also input voltage is changed to plus 10 volt, which means previously the capacitor should have charged to minus 10 volt. Then you will get at this node 20 volt. So this is not correct. If you assume this has some different scale, then this is minus 20 volt and this is plus 20 volt. So this is what we got the expressions. This is minus 20 e power minus t by tau, and this is plus 20 e power minus t by tau. So that is about these two expressions. So this is wrong. Yeah, this is not minus 10 and plus 10. This should be minus 20 and plus 20, right? So this is about this circuit. If we give some pulse input, in next lecture we will see what will happen if the RC value is much greater than the time period. It means we are not giving enough time for the circuit to go to its steady state. So at that case we will see what will happen to that capacitor voltage. Will it go to some any steady state waveform, or will it be oscillating to some different values? That we will analyze and check in next lecture. Yeah, if you like this video, then please share to your friends, and if you have any doubts, please comment down. Thank you.